Okay, so we were discussing about dispatcher. The dispatcher module, it is the one which is responsible for taking a process from the ready queue to the CPU. Okay, and it does these following things. It does the context switching, which means it loads a process. It loads the context of a process from its context, which is in PCB, into the CPU. But before that, it needs to save the process, the context of that process which was already running on the CPU. It is also responsible for switching the mode, the hardware bit, okay, which was in kernel mode because this dispatcher was running. So it will set that mode to the user mode. And finally, it starts the new program by pointing to the instruction in the program counter, and actually this is stored in the context in the PCB. So we need to minimize the dispatch latency. That's the important thing, because if the latency is more, it will be having a waste of some time in non-useful activities. The useful activity for us is the running of the process in the CPU. The context switching, etc., they are called as the overhead, okay, the non-useful things. So if we are going to choose an algorithm for scheduling, then we should consider some criteria, and these are the 5 criteria we are going to see. How do we select an algorithm? CPU utilization, throughput, turnaround time, waiting time, and response time. So a good algorithm must maximize CPU utilization and throughput. CPU utilization means to keep the CPU as busy as possible, and throughput means how many processes complete their execution in some unit time, for example in 1 second or in 5 milliseconds, etc. So the more number of processes complete their execution in the unit time, the better the algorithm is. Turnaround time is actually the time to execute a particular process on CPU overall. Okay, so this is the time from start until the end. Waiting time, how much time the process waits before it turns, its turn come on CPU. And response time is the start time when you have the new process until you get a response from the process in terms of like response when you click on the keyboard, let's say, or you see some screen from the process. So we need to minimize the 3 criteria, the last 3 criteria, and maximize the first 2 criteria. Last time we finished the first algorithm, which was the first come first serve, okay, and the idea is that you make a normal queue. Any process that comes, you add it at the end of the queue, and the process which is at the head of the queue, it goes to the CPU. So this queue we are talking is actually you can say that from ready queue. Okay, so from ready queue we are moving this process to the CPU. What we are doing in this example is there are 3 processes, P1, P2, P3. Each process has a burst time, and a burst time means the time it will spend on the CPU. So P1 has 24 time units, P2 has 3, and P3 has also 3 time units. So if we assume the order of P1, P2, and P3, then P1, it starts execution first for 24 time units, then it is followed by P2 and then P3. Overall, they take 30 time units, but the longest time is taken by P1, which is 24 time units. We calculate the waiting time. For P1 it is 0 because it started the first one, it did not wait at all. So for it, the waiting time is 0. P2 was waiting for finishing of P1, so it waited 24 time units, and P3 was waiting for both P1 and P2, so it waited for 27 time units. These are the individual waiting time for each of these processes. Then we find an average. We add the waiting time of each one and divide it by the number of processes. So the total waiting time is 17, which is quite high. Why is it high? Because in the other slide, if we change the order, we make it P2, P3, P1, then we can see the waiting time is reduced to only 3 units as compared to 17. And here you can see the reason is because in the first case, in the previous case, P1 was before these processes, so the other processes had to wait for a longer time. Here P2 and P3 were short processes, so P1 had to wait for a small time and the overall waiting time was decreased significantly. This is a problem in first come first served, which means that if there is a longer process which takes longer time to complete its execution on the CPU, so those processes which are shorter, they suffer from waiting for the longer process, and this is called the Conway effect. So it means that we should have a small waiting time. We can have a small waiting time if we arrange the processes such that the one with the shorter time of CPU burst, it executes first, and this gives rise to the next algorithm, which is the shortest job first algorithm or shortest job first scheduling. So what we do in this one is, for each of these process which is waiting in the queue, okay, for execution, we note its execution time that it wants on the CPU, which is actually the CPU burst, and then according to the length of the burst, we schedule the process such that the shortest CPU burst process, we take it first to the CPU and then the longer one and so on. Now this shortest job first algorithm, this is known as the optimal algorithm. Optimal means it can perform the best, it can give us the best results in terms of minimum average time for any set of processes with any CPU burst times. But the problem with this algorithm is that it is not possible or quite difficult to know the length of the next CPU request, okay, because a process can never know how much time it will execute unless there is some algorithm which can determine how much time each process will execute, but it depends on various factors, for example user input, etc. Okay, so it's very difficult to know the length of the next CPU burst time, and that's why this algorithm is not practical, but still we can use it to some extent. And here is an example of shortest job first. You see there are 4 processes, okay, each one has a burst time, and if we arrange these processes according to the shortest burst time, then P4 has the shortest, it has 3 time units, then followed by P1 6 time units, followed by P3 which has 7 time units, and finally the last one will be P2 because it has the longest burst time, which is 8. So if you execute the processes according to this condition, then you have these waiting times, that for P1 the waiting time is 3, okay, only P4 executed before P1, and the total time it waited was 3 time units. For P2 it executed after 16 time units, so its waiting time was 16. For P3 the waiting time was 9, and for P4 the waiting time was 0 because it was the first one to execute. We sum these waiting times, divide by the number of processes, which is 4, and we get 7. So here we see the waiting time is quite less. Now in this case you can see that once the process is on the CPU, it remains on the CPU, which means that this is a non-preemptive version. We can also have a preemptive version, which is called the shortest remaining time first. Now what does the preemptive version do, or how is it different from this non-preemptive version, is that in the preemptive version, which is the shortest remaining time first, we can remove the CPU if there is a new process whose burst time is less than this one. So here is an example of shortest remaining time first. Okay. What do we see here is that we have 4 processes. Each one has a burst time, but we also add here the arrival time, because if a new process arrives, we may preempt the existing process if the burst time of the new process is shorter than the existing process in the CPU. So we run this algorithm as following, that we start with the very first process which is available, okay, or if there are many processes available in the beginning, then we will choose the one which has the shortest time. So here only one process P1 is available at time 0, which has a burst time of 8. So we start with P1, okay, P1 goes to the CPU, and after one time unit we see that another process P2 has arrived, and when we compare the remaining time of P2, which is the burst time, it is only 4. And by this time P1 has done only 1 unit, so the remaining time of P1 is 7 and P2 is 4. Now 4 is less than 7, so we make a context switch and we bring in 4 time unit, which is actually P2, to the CPU. At P3 another process comes, we again make a comparison, and P3 at time unit 2, it has 9 burst time. P2 now has 3 remaining time units, because 1 time unit has already passed. P1 has 7 time units. So when we compare 7 and 3 and 9, then 3 time units, which is for P2, it is small, so the P2 continues execution. At time 4 we have another process, at time 3 P4 comes, its remaining time is 5, but because P2 is already less than 5, so P2 continues execution and it finishes at time 5. When P2 finishes, now what we have is the remaining process is like this. We have P1 whose remaining time unit is 7, P2 is finished, P3 the remaining time unit is 9, and P4 the remaining time unit is 5. So 7, 9 and 5, out of them P4, which has 5 time units remaining, we choose it and it goes for its completion until time 10. Then the remaining processes are P1, which has 8, and P3, which has 9 burst time units. So P1 is smaller, actually it was 7 because 1 time unit is done here before. So 7 time units, it is smaller than 9, so we choose P1, it executes when P1 finishes. After 7 time units we have P3. So in this way what we see here is we choose the process which has the smallest remaining time or shortest remaining time first algorithm. So how do we calculate the waiting time? We start with P1. Now P1 was on the processor twice, one here and once it was here later time. The overall waiting time, if you consider this one here, it was 0 for the first time, but it was removed and again from 1 to 10 it was waiting. So to calculate the final waiting time for P1, we will subtract this area, which is the waiting time. Okay, we will take this and subtract this one, which it was on the CPU. So this is 10 minus 1, which means that 9 time unit was the waiting time for P1. For P2, P2 came at time unit 1 and it went to the CPU also at time unit 1. So the waiting time was 0, 1 minus 1. For P3, it went to the CPU at time 17, but because its arrival time was at time unit 2, okay, it arrived somewhere here, so its waiting time was 17 minus 2, which means that 15. And for P4, it went to the CPU on time 17, okay, but it arrived, P4, it went to CPU on time 5, okay, but it arrived on time 3, so this is 5 minus 3, which means 2 time units. The sum of these 4 divided by 4, this gives us 6.5. It can be millisecond or whatever time unit we choose. So this is how we find the waiting time for shortest remaining time first. The next algorithm in this CPU scheduling is that of priority scheduling. What is priority? When you assign some value to a process and you choose the process for scheduling according to that priority value. Now here we consider that a priority value is an integer, okay, with each process, and this indicates if the process has a higher priority or a lower priority. Now here for this algorithm we consider that if integer is small, okay, then it has high priority, and a bigger integer has a lesser priority. So a priority of, for example, 1 is more important than a priority number of 2. Similarly, 1 is more important than a priority number of 10. So lower number means higher priority. And here, so what we see is that we give the CPU to that process which has the highest priority. If our priority number starts from 1, then 1 is the highest priority. This type of scheduling can be preemptive or non-preemptive. In preemptive, we can see that if a process is executing on the CPU and another process comes which is of higher priority, then we will preempt the process and give place to the process which has come now. In non-preemptive version, what we will do is that once a process is on the CPU, we will not remove it until its completion of its execution on the CPU. So an example is that if you consider SJF, the shortest job first, it is also a type of priority scheduling algorithm, but instead of giving a number, we give priority to the process which has the shortest CPU burst time. So the shortest CPU burst time of a process is there. We will choose that for the highest priority for execution onto the process. Now, there is a problem with priority scheduling. If we use some priority, let's say some number, okay, or even like some other things such as the shortest burst time, we will always have a problem which is called starvation. Starvation means that if there comes a process whose priority is very low, it may never get a chance to execute, because every time there is a chance to execute, some other process may come with a higher priority and that process will go to the CPU. So new processes come every time, and it might be possible that all the incoming processes, they have higher priority than this process which has a lower priority, so it will keep on waiting. This is a problem, and this is called starvation. A solution to starvation is called aging. Aging means that you increase the priority of that process which has a low priority. So initially it has very low priority, okay, but after some time you increase the priority of this process, and some time will come that all the new processes they are coming, they will not be higher than this process, and this process will get to the CPU. So starvation is a problem and aging is a solution to the problem. We see the example of priority scheduling like this, that we have 5 processes, and with each process we have the burst time as well as the priority of a process. And for this example we choose that every process has a different priority. Okay, if 2 processes come with the same priority, then we can choose anyone randomly, or maybe we can choose the one which comes before, first come first serve. So 5 processes with burst time and priorities, and we are going to give them the CPU. So we will see the priority of each process, and here we see that P2 has the highest priority. The priority number is 1, which is low, but low number means higher priority. So 1 has the number 1 is the highest priority. So we give CPU to process P2, whose burst time is only 1 time unit. After that, we choose the next one, which is the priority number 2 associated with process number 5. The process 5 executes for 5 time units. After that, we choose P1 with the priority 3, then P3 with a priority 4, and finally P4 with a priority of 5. So if we find the average waiting time, then it turns out to be 8.2 milliseconds. So this was priority scheduling. We have priority number for each of the process. The next algorithm for process scheduling is known as round robin. Okay, here how does it work? Each process gets a small unit of CPU time, which is called time quantum or Q. So a process will try to execute during this time quantum and finish its task. Okay, if it can finish during this time quantum, well and good, this process can be terminated. But the problem comes if this time quantum expires, which means the time given to this process finishes and the process has not yet completed. So in that case, we will remove the process from the CPU and we will put it back at the ready queue at the end. This way it will have to wait for all those processes which are before this process, and when all those processes are finished, then it will be its turn. So how much time we normally give for time quantum? Usually it can be anything between 10 to 100 milliseconds for each process. And how much time, maximum time a process can wait? So it depends on queue and the number of other processes. Let's say total processes are n. So a process, any process which has to wait for the queue, it will be waiting for at most n minus 1 processes. Before this process, there can be at most n minus 1 processes, and it has to wait for each process before its turn can come. And how much time will it be? So if each process can have a maximum of q time units, so it can wait a maximum of n minus 1 multiply q time units. Okay, why q? Because let's say q is 10, so each process will have 10 time units, multiply the number of processes before this. That's the upper bound or the maximum time it has to wait. So we use a timer which will generate an interrupt whenever the time quantum expires, and then the dispatcher will actually bring in the next process to the CPU. Now if we discuss the performance of round robin, then there are two, the important thing which affects this algorithm is q, the value of q. If we make q very large, then this algorithm will become like FIFO. Why? Large q means that most of the processes will have a burst time which is smaller than u, so they will be able to finish their processing. Okay, and it means that the rest of the processes they have to wait, and this will simply become a first in first out. If q is too small, on the other hand, then the problem will be that you will take your time in context switching, because it means that there will be more context switching. Large q means little number of context switches, and small q means higher number of context switching is done. Now if you do too many context switches, it means that you are wasting your time in useless activity which is not counting towards the productivity of the process. So too large or too small, both are not good. If we consider the q to be 4, the time quantum is 4, and we have these 3 processes, then you can see that the gain chart which shows each process execution can be something like this. We start with any process randomly, let's say P1. It executes only for 4 time units, although its burst time is 24. It requires 24 time units, but we will only give CPU to one process for time q, which is 4 here. P1 will execute for 4 time units. After that, we have P2, which will execute for 3 time units, because that's the maximum. Then the next turn is that of P3. P3 also has 3 time units. It also finishes before its time quantum, and then only remaining process is P1. So we continue with P1 one by one. So every 4 quantum, the scheduler checks if there is a new process. If there is no new process, only P1 is remaining. So it will keep executing for 4 time quantum, and after each time quantum break, the CPU scheduler will check for new process. If there is no process, P1 will keep continuing the execution. So the problem is that the turnaround time is higher than the shortest job first. Okay, because of the context switching, the process can come out, go in, so it takes longer to complete each process, but it has a better response time. Okay, Why is it better? Because each process is coming to the CPU very quickly. The process does not have to wait for long before it can get the CPU. So the important thing is that the Q, or the quantum time quantum for one process to be on the CPU, it should be large compared to the context switch time, because if it is not very large, then it will be taking the same time as context switch, which is not good for performance. Normally the Q is between 10 to 100 milliseconds, okay, the time for which a process executes on the CPU, and the context switch is less than 10 microsecond. Okay, so context time is usually about 1000 times lower or smaller than the Q time. So this diagram compares what will happen if we change our quantum time. So in the type 1 we see that the quantum is 12, okay, and let's say the burst time is 10 units, the process time. So if the quantum unit is 12, quantum is 12 time units and process time is 10, it means that the process will finish before any context switch. Okay, so there will be no context switch in the first example. If we make the quantum to be 6, then there will be one context switch. As you can see in the second example. And finally, if the quantum is 1, so we can see that to complete this process, it will make 9 context switches. So the context switching, you have to decide on the one which is better, which performs in, which results in good results for not just one process but many processes for interleaving to give us better performance. Here we discuss just a brief discussion on how turnaround time varies with the quantum time. If you remember, turnaround time is the total time taken by the process, okay, to finish its execution. So we see that although the time quantum should be large compared with the context switch time, it should not be too large. If it is too large, then the round robin scheduling or RR scheduling, it becomes an first come first serve policy, which is not good. So what do? Is we have this rule that 80% of the CPU burst should be shorter than the time quantum. Okay, quantum, which means that time quantum should be big enough so that 80% of the processes can just finish their job in one CPU burst. Next type of scheduling, the algorithm, is multi-level queues. We know about a queue. Normally, until now, we have considered only one queue, which is the ready queue. But what we can do on improving the queue is to partition the queue, or to have more than one ready queues. And each of these new ready queue will take up special type of processes. For example, one can be foreground queue, the other can be background queue. And what we can do is to give the foreground queue only interactive processes which require high response time. Okay, and we can put the batch processes in the background queue. Batch processes are those which execute one by one. They may be lengthy, they may be slow, okay, but at least they don't need user interaction. They can run in the background, okay, without any user involvement or without the user for need of any response from the batch processing. So we can call these the background processes. Now, if we assign, one of the assumptions can be that if we assign a queue to a process, then that process will be permanently in that given queue. It will not change its queue from one to the another one. Okay. Now, what we can do is that, let's say there are two queues, so we can assign a different algorithm, scheduling algorithm for each of the queue. For example, the foreground process which requires interaction, which requires better response time, we can give it round robin, and the background process, because they are long and normally they are not urgent, so we can give them the first come first serve scheduling. Okay. Now, if there are more than one queues and there is only one CPU, which is our assumption, so how can we assign a process from one of these queues to go to the CPU? Because we have two, let's say in this case we have two queues, so should we choose the next process from the foreground queue or the background queue? So scheduling must be done between the queues, and we can see that there are some possibilities. One is fixed priority scheduling, which means that first we serve all the processes from the foreground, and when it is finished, then we go to the background. Okay, but this can give rise to starvation. What does it mean? It means that those processes which are in the background, maybe they never get a chance because only foreground processes are running. So we can have a time slice where each queue it gets a certain amount of CPU time. Let's say 80% of the time can be given to the foreground and 20% can be given to the background. Okay, and the foreground can be scheduled using the round robin, and the background can be scheduled using the first come first serve. But this is just an example, and we can have any other possibility. Okay. So in the algorithms before, we had only one queue. In multi-level queues we have different queues. Okay, an example is this multi-level queue scheduling. You can see here are 5 queues, and each queue has a set of processes according to their priority. So for example, the system processes which have the highest priority, they go into the system processes queue. The second highest is the interactive processes queue, which have those processes which are interactive. Then you have interactive editing processes. Okay, let's say Microsoft Word, for example. Then you have batch processes which execute in a sequence. And finally, we see here that the student processes, they have the lowest priority. So when a process comes, it must be in one of those categories, and you put that process into their queues accordingly. Now, a process can move between the various queues, and then this way we can implement aging. Okay, how? Let's say a process is in one queue, it has a low priority, and after some time the process is still in that queue and it has not its turn. So we will promote this process to another queue where there is a higher chance. Still, if number is not there, its turn, then we will move it to next higher level, and so on until it gets its chance. So if you have a multi-level feedback queue, okay, so I forgot to tell you that what we are talking here is the addition of feedback to this queue. So normally this one is without any feedback, and here we see is a feedback we introduce a feedback system, which means that the processes can move between those queues. So in multi-level feedback queues, we define the number of queues which are there, which is the algorithm for each queue, okay, and which method can be used to move a process in case of upgradation from one queue to another, or to demode a process, which means that reduce its priority. And we also decide which method to use to determine that when a new process comes, in which type of queue will this process enter. So we see this example of multi-level feedback queue. We have 3 queues, Q0, Q1, Q2. Q0 is a queue which uses round robin, and it has a time quantum of 8 milliseconds. Another queue is also round robin, which uses a time quantum of 16 milliseconds. And a third queue which simply uses first come first served. So how do we do? We start with a process. Every process enters into Q0. okay, and actually itself it is first come first served. So any process that comes, it will directly go to Q0 without any scheduling outside, okay. But then it will be served with this time quantum of 8, which means that if this process finishes its burst within 8 quantum, then it will go and it will finish. Otherwise, if it is not finished, it will go to the next queue, which is time quantum 16. Similarly here, if this process finishes within 16 quantum, it will go out, it will finish. Otherwise, it will become a part of the last queue, which is the first come first serve, and it will wait for its turn, and then it will complete its execution in this queue. So that was the end of the different scheduling algorithms. Now we come to the multi-core processor topic. Why we discuss multi-core here? Because these multiple processors, having multiple processors in a system, it affects your scheduling algorithm. Okay, so what is a multi-core processor? We have already discussed this in chapter 1, but to repeat, multi-core processor means that there is a trend that on one physical chip you have more than one processor or cores. So it can be 2, it can be 4, or let's say it can be even 8. Okay, so why is it important? Because if you have many cores on one chip, it means that it is faster. Okay, the communication between them is faster, and they consume less power because they are very close to each other, so the data moves faster. Then there is another trend which says that multiple threads can be executed on one core. For example, one thing is that if you have dual thread, 2 threads on one processor, so we have something which is called memory stall. Memory stall is the time during which the CPU brings data from the main memory to the cache, okay, and in this time the CPU has to wait for the data, so it cannot execute any instruction. So what we do is that if there is a memory stall, which means that the CPU is waiting for the data to come from main memory to the cache, in this time we can load another thread, and this thread is ready to be executed, so it will start execution. So this memory stall affects your scheduling scheme such that if there is a memory stall, you can do a context switch and bring in another process. So it means that the processor is working on multiple threads almost at the same time. So how does it work? We can see here this example. Okay, we have 2 diagrams, one on the top, okay, which is only unithreaded processor, which means that only one logical thread is executing, and the other one is dual threaded processor core, which means that we can have 2 threads for that processor, and we call them the hardware threads. Okay, it is managed by the hardware. So in the first case, when a process or a thread, actually we are considering thread here, it finishes its compute cycle or it's waiting for memory stall, so the CPU is not doing anything, the CPU is only waiting for the memory stall, during which we load the cache with more data from the RAM. In the second case, we can utilize this memory stall that if thread 0, it is doing its computation cycle, and then there is a memory stall during which thread 0 has to wait, so the CPU does not wait, rather it loads thread 1, and thread 1 is executing instead of thread 0. During execution of thread 1, the memory stall is actually applied and the data comes to the memory. Okay, so the CPU can then bring in the thread 0, but it does not bring in the thread 1, keeps continuing until it reaches a memory stall. So memory stall for thread 1 means that thread 1 has to wait, so the CPU loads again thread 0, and in this way the CPU switches between thread 1 and thread 0, and it is almost always doing some execution, so it does not have to wait. This means that if you consider these two diagrams, in the first diagram, after the same time, we are able to finish only one thread, and in the second diagram, two threads, they are executing at the same time. So this is almost 50% faster speed. Okay, this is called actually taking benefit of logical processor, logical hardware threads. So this issue of multi-threaded multi-core system is solved using this solution. Now briefly in the next few slides we are going to discuss about Windows scheduling. How do we do scheduling in Windows? Now Windows uses what we call the priority based scheduling. Each process has a priority. But Windows also uses preemptive scheduling, which means that if there is a low priority process running in the CPU and another process with high priority comes, so we make a context switch and we bring in the process to the CPU which has the higher priority. So the highest priority thread will run, okay, and here we have the dispatcher which acts as a scheduler. So the dispatcher itself decides the scheduling, okay, using the priority based preemptive scheduling, and a thread will run, okay, until either it blocks, which means that waiting for some IO, it needs some IO, or it uses its time slice which is given to it, or number 3, it is preempted by some higher priority thread. Now what we see also is that real-time threads, they can preempt non-real-time threads. So we differentiate between two types. One is real-time, the other one is non-real-time. Overall, there are 32 levels of priority scheduling scheme to determine the order of thread execution. And priorities are divided broadly into two main classes. One is the variable class, which contains threads which have priority from 1 to 15, and the real-time class, which have threads whose priority range from 16 to 31. So here we see that the highest priority or the most important priority is 31 and the least priority is 0. Okay, we are going to see what is 0 in the next slides, but that is the least priority. So unlike what we studied in the priority scheduling, where we discussed that priority 1 is higher, priority 10 is lower, in Windows priority 1 is the lower and priority 31 is the highest one. So the dispatcher, it uses a queue for each of scheduling priority, okay, and it traverses the set of queues from highest to lowest until it finds a thread that is ready to run. So for example, the highest priority is a real time number 31, so it goes to that queue and it sees if there is a process, in that ready queue, it will run that process. If the process is not there, then it will go to the next highest priority, which is actually 30. If there is any process in the queue 30, it will execute, otherwise it will go to the next lower priority and so on. And if there is nothing to be done, all the queues are empty, then the dispatcher will execute a special thread which is called the idle thread, which has priority 0, okay, and that is actually about memory management thread. If no other process is executing, so the priority 0 process, which is memory management, it will execute, otherwise it will be an idle thread, it will not do anything. So the summary, we have here the priority classes for Windows. Okay, we have you know about Win32 API, we discussed it before. Win32 API, application programming interface, is provided by Microsoft for writing Windows programs. Okay, and here in this Win32 API we have these priority classes: real-time priority class, which is the highest, then you have high priority, above normal priority, below normal, and then the idle priority. These are the 6 priority classes, and they are all variable, which means that they have their values between 1 and 15, except the real-time priority, which has values above 16 until 31. Similarly, within a priority class, you have 5 different levels, which means time critical, highest, above normal, normal, below normal, lowest, and the ideal priority within each class. Okay, so overall 6 multiplied by 5 they give you 30 plus the 0 1. These will give you a combination of different priorities. By default, each priority is normal. Okay, and if the time pointer expires, then the priority for that process is lowered, but never below the base case. So if you start with highest priority and the highest priority cannot finish in the time quantum, so you reduce it to high priority and until it gets to the normal. So this table actually summarizes all those priority. In the real time class, the time critical has the highest priority, which is 31. Then the next is in the real time class, which is the highest critical, which has 26 for example, and the lowest priority is in the ideal priority class, which is this one. With the ideal process, it has the priority of 1. So in these cases you can see that all these, which are the variable classes, okay, they have priorities between 15 and 1, and the real time processes have the priority from 16 to 31. Okay, so this is the end of chapter 6. Do you have any question in chapter 6?